so today we start, in some sense, we go into the core of the course. What we've done so far in the last couple of weeks has been a little bit of introduction and basic concepts, and then we've introduced the definitions of invariant measure, ergodic measure, talked about the properties of invariant and ergodic measures, and today we're going to put these properties in practice to study specific examples of dynamical systems in a more sophisticated way. Right? So the first class of examples that we're going to look at today is a class of examples that have just one invariant measure. So this is sometimes known as unique ergodicity. So we say definition, F is uniquely ergodic. If it admits a unique invariant measure. So as we saw, of course, in many examples, there are many invariant measures, right? Like in the example 10x mod 1, if you have many fixed or periodic points, that every fixed or periodic orbit supports an invariant measure. So in general, there are many invariant measures, but there are some special examples that only have one, and they have some kind of special characteristics, so we focus on them today. And of course, if you remember, the ergodic measures are the extremal points of invariant measures, so if there's only one invariant measure, it has to be ergodic as well, right? So unique invariant measure, which is therefore ergodic. So the most trivial example is, as we've seen before, if you have a contraction of a complete metric space. Contraction, right? So it has a fixed point P, and every point converges to P. Right? So a fixed point P, if you take any initial condition, it will eventually converge to P. That is the simplest case. So this has delta P, we've already seen, is invariant and ergodic. You can come in. Yeah. I'm sorry that maybe there was some confusion with the dates. I apologize. I don't know if this is why you're late or it's independent of that.
No, sorry, the bus didn't pass.
Okay, no problem. No problem. Glad that everyone came in the end. Is that okay? So how do we know in this case that there can be no other? How do we know? So here we know there's a fixed point. So we know that there exists one ergodic invariant measure. How do we know that there can be no other invariant measures in this case? We need to use some of the results that we have been discussing about invariant measures. So we have a contraction of a complete metric space. Every orbit converges to the point P. Why can there be no other invariant measures except Dirac delta P? be fair, I have to say that it's not, now that I think about it, we did not state, the result I'm thinking of using to show this, we did not state in its full form. Okay, I will say in a second. So we stated it in a limited way. The way we stated it did not give us exactly this, but there is a further statement. Does anyone have some ideas of how we could argue this? I realize now that maybe I've not given you all the ingredients we need. But almost. So if there was another invariant measure, it would have to give positive measure to some other regions of space, right? So there would need to be some other set A which had positive measure, if there was another measure, right? Suppose there exists mu invariant measure in F, with mu is different from the Dirac delta in P. Right? Then there must exist a set A that does not contain P. Okay. In X, it does not contain P with positive measure. So what do we know about sets with positive measure for an invariant measure? Sorry? Poincaré recurrence. What does a Poincaré recurrence say?
That if such an A exists, then for almost every point, it should come back sooner or later to the same. But if it's contraction, all is going to be.
Exactly. Right? So, if we can obviously choose this set A which is separated from P, right? And so all the points of this set A, so if you want to be really strict, you should need to use what the full Poincaré recurrence theorem says is that almost every point comes back infinitely many times, right? I put in the notes this addition. I think I forgot to mention that the proof is not an immediate corollary. You need to adapt the proof a little bit, but it's not that complicated. So the Poincaré recurrence theorem says actually that you come back infinitely many times. And of course this cannot be in this case, right? Because if you have a set A here, depending on how, so in some sense you can believe it also that it contradicts the fact that it needs to come back once time, because you can choose an A, that maps outside itself and never comes back. But if you want to be more, formal without any other additional consideration, the full Poincaré recurrence theorem says that almost every point comes back infinitely many times. But if this set here does not contain a neighborhood of P, which we can clearly also choose that. So maybe I should say this is outside some neighborhood of P. And then these points will eventually be inside this neighborhood, and so cannot come back to A infinitely many times. So by Poincaré recurrence, almost every X in A returns to A infinitely many times. but this is impossible since all points converge to P. So this is one of the examples in which even a very simple statement like Poincaré recurrence gives some conclusion. So recurrence, the concept of recurrence is that points come back, and when you have just a contraction, everything converges to P, you don't have any recurrence anywhere, except the point P itself stays where it is, but every other point in space will leave a neighborhood of where it is and will approach arbitrarily small neighborhoods of P, right? So every other point just goes towards P and never comes back. This is why the contractions are simple, and there can be no other invariant measures except for delta P. So this is a simple example of unique ergodicity. Any questions? Okay. However, we're interested in much more sophisticated examples. And so the main theorem we're going to prove today is, or one of the main theorems, is the following, is that if f S1 to S1 f of x equals x plus b mod 1 is an irrational circle rotation, so b is irrational. Okay, so this is an irrational circle rotation. So do you remember what we have already proved about the irrational circle rotations? Topological structure of these? Do you remember, do they have periodic points? What's the dynamics here? Dense orbits, exactly. Every orbit is dense. Okay? That's from a topological point of view. And what we're going to prove is that they're uniquely ergodic. And what is the invariant measure? So there's only one invariant measure, which we know what it is already. What is it? The Begg measure. When B is rational, the Begg measure is also invariant, but is it ergodic? Remember, when B is rational, what do we have? Sorry? Periodic orbits. That's right. We have every orbit is periodic. So not only is it easy to see that the Begg measure is not ergodic, because you can easily find a small arc of the circle that comes back to itself, which is periodic, and so it has positive measure between 0 and 1. It's not invariant. And also there's lots of other ergodic invariant measures on all the periodic points. Okay, so if it's rational, it's absolutely not uniquely ergodic. But if it is irrational, it's uniquely ergodic. It's not that surprising. As we go through it, it's a non-trivial example, but it's not surprising because as we shall see, the circle rotations are very rigid, and it's not surprising that everything does the same thing. So one of the advantages of proving that it's uniquely ergodic is that we know, like we did before, once we know one invariant measure, which is the Begg, we know there cannot be any others, right? So that's the only one. However, one of the most interesting aspects of being uniquely ergodic is that there's a very strong rigidity. And I'm going to state here as an important result of our uniquely ergodic maps. So suppose F is continuous and X compact matrix space. And suppose F is uniquely ergodic. So that it has one unique ergodic embedded measure mu. Okay, then for all continuous functions on X, we have that the limit and the sum of these functions in xi is equal to the integral of phi in mu, which we will write for simplicity as phi of f for all x0 in x. So what is the difference between this statement and Birkhoff's ergodic theorem?
The phi doesn't depend on the.
Excuse me?
The phi does not depend on the initial point.
Exactly. So not only the phi does not depend on the initial point, but this convergence holds for every initial condition, and not just for mu almost every initial condition. This is a very important and major difference in this case, right? And this, as we shall see, will really come from the unique ergodicity. The unique ergodicity implies a lot of rigidity. It implies that you can go from almost every to every, because there's no, more of it's because there's no other measures. There's no other measures to which this can converge, right? So there's only this, in some sense, only this invariant measure, but we will see in the proof how this works. So in particular, if you remember our definition of basin, in particular this means that the basin of mu is the whole space. Right, so if you remember, we introduced the concept of physical measures, and the concept of a basin is exactly the set of points for which this holds. Right? So here this holds for every initial condition, which means that every single point is in the basin. Of course, this also holds trivially here. You can easily verify for contracting fixed points, but it will have some interesting implications when we apply it here. It will be, in particular, so as a corollary of this, we will get that for F irrational circle rotation, and if we take an arc then we look at every single orbit is uniformly distributed. So we know. So if we look at the number of indices between 0 and such that xi belongs to this arc AB, right? And we divide by n. Okay, this is the usual. So you look at the orbit and you look at the frequency, this converges to the length of AB, okay, to the Lebesgue measure of AB, just A minus B, okay, for all initial conditions. This is the difference from the Birkhoff-Ergodic theorem, right? In the case of 10x mod 1, which is the map which we're going to go back to tomorrow, is going to be really our main class of examples. Of course, that is not true, right? We will show that for 10x mod 1 and other similar maps, Lebesgue measure is also invariant and ergodic, but it is not uniquely ergodic, obviously, because also in those cases you have coexistence of lots of periodic points, right? And of course you can take a fixed point, and a fixed point is not going to satisfy this condition with Lebesgue measure, right? Even if Lebesgue measure is invariant and ergodic, Birkhoff's ergodic theorem will tell us that we have this for almost every point, but not for every point. And in some cases that's really important, okay? Especially because sometimes you don't know which point. If you just take an arbitrary point, you don't know if you got lucky and you got one of these good points, or if you got another point. Okay, so this is going to be the results we're going to prove today on unique ergodicity. But I think for the rest of this first half, I want to give a nice little application. So there's a lot of interesting applications of ergodic theory to other areas of mathematics. So dynamical systems in general and also ergodic theory are very interdisciplinary subjects. That's one of the reasons why I like it so much. They are interdisciplinary because they involve a lot of techniques from different areas. In this particular course, we're not applying very sophisticated techniques. But if you go on, you see that there are results from function analysis that come in, from measure theory, from topology, from differential geometry. There's a lot of fields that come in because sometimes you're looking at the dynamical systems on manifolds and the global topology of the manifolds as an effect, and all kinds of structures come in. But the nice thing is that it also has applications. So results in dynamical systems, really, you can use techniques and results in dynamical system to prove results about other fields. And one of the most is number theory. There's a lot of results in number theory. I'm absolutely not an expert, but there's a few very simple ones, okay? And in particular, there's quite a nice little application of this one here, of this unique ergodicity, which I want to describe. And to define this, so this is called Benford's law. I don't know if any of you have ever heard about Benford's law, probably not. So the main concept in Benford's law is that of a leading digit of the number. So if we take a number A, any real number, we define D of n is a leading digit, and this means the first non-zero digit. Okay, equals the first non-zero digit in A. So if A is bigger than 1, then the first non-zero digit is just the first digit of A. But if A is between 0 and 1, like 0.007 something, then 7 is the leading digit, right? You just look at the decimal expansion and you wait till the first non-zero digit. This is called the leading digit. And the question is, given a set of numbers, a set A, in principle just a set in R, what is the statistics? Let's say that it's finite or countable for our purpose, right? Finite or countable. What is the frequency So this seems like a very strange question. There's no reason why there should be any particular distribution of the leading digits if you have a set of numbers. But as it turns out that there's some scientists in the 19th century. So apparently, this is what I hear from the history of this, is that there was a astrophysicist, astronomer, Simon Newcomb in 1880s. He noticed, that in the old times they had these logarithm tables, books where you look up the logarithm before computers, right? And he noticed that certain pages were much more consulted than other pages, right? And it turned out that there were the initial pages with numbers kind of starting with 1, where the leading digit was 1. And then other people like Frank Benford, he noticed that there was a lot of data. If you looked at big data at the time, not as big as the big data we have now, but for example, especially if it was data that spanned different scale, different orders of magnitude. If you looked, for example, at the size of different towns and cities in the US, I think he did this study, and he took the list of all the cities and small towns, big towns, villages, and you take the list of all the population sizes. So this is just a random list of numbers that seems to have no connection. And he noticed that the leading digit 1 seemed to occur much more often than the leading digit 2, more often than the leading digit 3, and so on. He noticed that there was some kind of distribution. And in fact, he noticed that 1 in many situations turned up about 30% of the time, 2 about, 17% of the time. So let me, let me write here what we define as Benford's distribution. Take a sequence AI, infinite sequence, has a Benford distribution. If for the 1 to 9, so the leading digit is something between 1 and 9, right? We have what we call d of d, which we will define as the frequency of this leading digit. And it's a limit presenting to infinity of the number of times that the leading digit of AI is equal to t. Right, so we fix d between 1 and 9. We look at this sequence, and this is now familiar. This is just a proportion of elements in the sequence where the leading digit is exactly d. And we want this to be equal to log base 10 of 1 plus 1 over d. So it's easy to check that the sum log base 10 of 1 plus 1 over d equals 1 to 9 is equal to 1. Right? So this is really defining a kind of probability distribution, right, on this. So it's saying that each digit occurs with a certain probability exactly with that probability, right? So it's saying that the limit exists. Here we have, you can calculate this, so b of 1 is roughly 0.3, B of 2 is roughly 0.17 and so on, and then B of 9 is roughly 4%, that's 0.04. Right, so you can calculate these precisely. Again, this is just dropping out of the sky, right? There's no reason why this should go. We've just chosen a certain weight, you know, on all digits, and we say, okay, this sequence, this is a definition that is empty. If you just look at it as a definition in the sense that, okay, you know, we want each digit to occur with a certain frequency. And what would be interesting is that there's a very natural sequence which has this frequency, superposition. That K in N, so the K is different from 1, and K is not a power of 10. So any integer except 10 to some power. Okay, then the sequence K to the N, n equals 1 to infinity, has Bamford's distribution. Right, so for example, the sequence, if K is equal to 2, then this is the sequence 2, 4, 8, 16, 32, and so on, all the powers of 2. Of course, when you look at it like that, there is absolutely no reason why you should expect the first digit of the sequence of numbers to have any particular statistical distribution. Any questions? Okay, so I think what I will do, I will now first prove this proposition. It's fairly simple proof, then we take a little break and then we will go back. So this is a corollary of these theorems, mainly of this theorem, of this corollary here in this theorem. It's an application of those results. And that's why I think it's interesting to present here. Okay, these quite abstract, seemingly abstract results for unique ergodicity, they have these really quite surprising concrete applications here. So, the proof is actually quite simple. So lemma so we're interested in this sequence here, right? K to the n. So our first lemma is going to say the following. The sequence sequence n, okay, the sequence log base 10, okay, to the n. So if we take log base 10 of each of these, sorry, log k and mod 1 is uniformly distributed. In S1. And why is that?
Irrational translation.
It's an irrational notation, right? Because this is just n log 10k, so through. So log base 10 of k to the n is equal to n log base 10 of k mod 1, right? And so this is just rotation. This is just multiplication. So if you take b, so this is this is equal to, so let x0 equals 0, right? xn equals n b mod 1, where b is equal to log base 10 of k, right? So this is just the orbit of the point 0 under the irrational rotation, right? xn is equal to, the orbit of the point is just this point plus translation by b each time, right? So if we now take b equals log base 10 of k, then the orbit is just the points n, b, n log base 10 of k, and if k is not a power of 10, then this is irrational. Okay, this is not rational. This is irrational, it's easy to check, and therefore it's uniformly distributed by this corollary. Right? So this is really, this sequence here is a sequence of points on the circle because it's mod 1, and it is exactly the sequence given by the orbit of the point 0 under the circle rotation of angle log base 10 of k, which is irrational. Okay, so it's dense in S1, and in fact it's uniformly distributed. And how does this help us? So the key point is the relation between this what's the relation between this uniform distribution and Benford's law? So lemma 2. Let AI be any sequence. Suppose that the corresponding sequence log base 10 of AI mod 1 is uniformly distributed. In S1, okay, by uniformly distributed, I mean this. Then the original sequence has Benford distribution. Sorry about my writing here, I know it's not perfect. Okay, so I wanted to state it as a general fact because this is what, so this is a particular example, right? So we have here, the example is designed, of course, to be applied to this. So we have a sequence that we're interested in, which is this, okay? We've shown that log base 10 of that sequence is uniformly distributed, and this lemma says that if log base 10 of your sequence is uniformly distributed, then the original sequence satisfies exactly Penfold's distribution. So how is that going to happen? Any ideas? It's not immediate to see, but it's not that difficult.
The first digit of log base 10 of AI is the logarithm of the first digit of AI.
So I couldn't hear what you said.
The first digit of the first sequence
Yes,
is the logarithm of the first digit of the second sequence.
that's right. And so, sorry, the first digit?
Of the first sequence
Yes,
is the first digit of the...
because
is
you're
the
taking logarithm base 10.
Yeah, and mod 1 you just add you just multiply by powers of 10, so
That's right. So basically this is it. So the first observation is that if the leading digit of AI is equal to D, okay, so suppose your number starts with 7. What does that mean? So these are all these are all numbers bigger than 1, right? So we don't have decimal places. So this is some integer, this is some number. So suppose it's 7. If it starts with 7, then it's going to be 7,000 something, or 7 million something, or 7 billion something, right? It's going to start with 7. So that means we can write it as D times 10 to the J plus something, right? So it means that our element AI is strictly between D10 to the J and D plus 1 10 to the J for some J. Some integer J. We agree with this? Yeah. So if it's 7, then it's going to be between 7,000 and 8,000, or 7 million and 8 million, you know, 7. So it starts with a 7 or with a D, right? And then this, taking logarithms base 10, this gives J plus logarithm base 10 of T less than or equal to logarithm base 10 of AI, which is less than or equal to J plus logarithm base 10 of D plus 1. Sorry, this is, yes. Yeah, just taking log base 10 of everything. And now I take mod 1 right, so this means, notice that J is an integer, right? And log base T is between 1 and 9, so this is a number between 0 and 1 each time, right? The log base 10 of D for anything between 1 and 9 is between 0 and 1, right? So when I take everything mod 1 here, I'm going to take log base 10 of A mod 1, which means I just take the decimal part, and this is less than or equal to log base 10 of d plus 1 and greater than or equal to log base 10 of d. Right? This is an equivalence in both directions, right? So the leading digit of AI is equal to d if and only if log base 10 of AI is between log base 10 of d plus 1 and log base 10 of d. Okay, so really we have rewritten by very elementary arguments the property of this large integer having a leading digit d with some characteristic of the log base 10 mod 1 of that integer. Right, which is not essentially what you said about the leading digits. And then how do we, okay? So then that's it, right? Because now we know, so you can partition. So now what we're interested is in the limit as n tends to infinity, or we said the number of times I between 1 and n, maybe, okay, it doesn't really matter of course, but just for consistency, like between 1 and n, doesn't matter. Between 1 and n, such that di equals d over n. Now this is exactly equal to limit as n tends to infinity of the number of times in which this holds, right? In which number of times number of indices between 1 and n, such that log base 10 of AI mod 1 is contained in the interval log base 10 of d log base 10 of d plus 1 divided by n. So if you think about what these log d's are all disjoint intervals for different d's, right? Because when you take d equals 1, you get log 1 to log 2, then you get log 2, when d is equal to 2, you get log 2 to log 3 to log 4, and so on. And this is exactly a partition of your circle, right? There are all disjoint intervals for different d's between 1 and 9. So we're interested in when this term is in this particular interval, and if by assumption this is uniformly distributed in S1. Right? So what does that mean? That means that, what does it mean about this limit? If it's uniformly distributed, remember it said that the frequency of times that it falls in an interval AB is equal to the Lebesgue measure of that interval. Right? So this means that this limit is exactly the Lebesgue measure of this interval here. So the Lebesgue measure of this interval log base 10 of d log base 10 of d plus 1 which is just this is just an interval, so this is just log base 10 of d plus 1 minus log base 10 of d, right, which is exactly equal to log base 10 of d plus 1 over d. which is exactly equal to log base 10 of 1 plus 1 over d. Okay, so we have used the uniform distribution of the sequence log 10 AI mod 1 uniform distribution to show that it must, the frequency of visits to each of these intervals is the Lorraine measure of this interval, which means exactly this. So the frequency of visits is the proportion of times when you take n very large, asymptotically, the proportion of times that this is inside here converges exactly to this value, right? So the probability, the percentage or the probability of being inside this interval is exactly this, and this corresponds exactly to having this as the leading digit. And this concludes the proof, right, of the proposition, because in particular, our sequence AI is this sequence here, k to the n, right? We've shown here that log of 10k to the n is uniformly distributed, using the fact that we know that the orbits, every orbit of the national circle rotation is uniformly distributed, and we need to use the fact that every orbit is uniformly distributed, because this is the orbit of a particular point 0, right? If we just had almost every orbit, then we wouldn't know if this particular orbit had this property. So this is uniformly distributed, and therefore we get this sequence. We get this frequency. Okay. Any questions? Okay, so I think this is a good time. Let's take a 10-minute break, and then we will come back and prove the unique ergodicity theorems that I stated.